Proof that shows that if you know absolutely nothing about the data, if the data is completely unbound, let's say you're going to be sorting some numbers and there's no limit on the numbers, then you cannot do better than theta n log n in doing that sort. Because, well, that's all we would call a comparison-based sort, because the only way you'd get to order those elements is by comparing them. And it turns out you really cannot do better than theta n log n on a comparison-based sort. Now, if we decide to put some limits on the data and restrict the things we're going to sort, it turns out that we can actually do better. One example is used, we call a bucket sort. Now, the radix sort is an example of the bucket sort. In the radix sort, while we're sorting, we are looking through the elements that we're going to be organizing, and we'll be making several passes through. Now, each time we make a pass, we look at the data and we just drop the item being looked at in one of several buckets. Now, in the radix sort, we decide that we're going to be sorting these values. So we're going to sort. One, 0, 2, 4, 7,
5, 8, 7, 1, 2, 7, 2, 0, 8, 7, 6, 2, 0, 8, 7, 6, 1, 5, 7, 3, 2, 9, 900 and 900, 2, 0.
Using the radix sort. So with the radix sort, we get the number of buckets that we get would be determined by the number of digits that we're sorting. So we're going to be making certain passes through the array, and each time we make a pass, we're going to be sorting the items in a particular position. So in the first pass, we're going to be just looking at the ones. So pass 1. After pass 1, we end up with the items in the ones column sorted. So that will be there first. Then the 6s will come out. Then no 5s, no 4s, no 3s, 2s are there. Basically, you'll be going through and say, okay, you look at the 1 column, it's a 7, drop it with the 7s. Look at this, drop it with the 2s. Look at the 6, drop it with the 6s. Look at the 2, drop it with the 2s. 0, drop it with the 0s. So each thing goes into the bucket, and because you have these spaces in memory that you call the buckets, and you simply just have to assign these values to those buckets based on the value, it's pretty quick. So to go through, so it's pretty much a constant time operation to assign a value to a bucket. So to actually make one pass through the array of n items, that's a theta n operation, right? So then we have 5, 8, 7, 1, 2, then 1, 5, 7, 3, 2, then 9, 0, 0, 2, 0. Pass 2, so that involves sorting this one on pass 2.
76 first.
When you sort the 10s, so in the 10s column, the 7 will come up first. Sorting that column. Then
4, 7, 1, 0.
And the 5s, and no 6s, no 5s, there are 4s. There's a 3.
Yeah.
2, and there's a 1. Now in pass 3, going to be sorting the third digit. So there's a 8 in that column, which is the biggest one in that column. That will be written out first.
Maybe 7.
Then there are 2 7s. And I'm going to be careful not to swap the sequence. Whichever sequence they were in before, I'm going to make it stay. 5 8 7 1 2. Then no 6s, no 5s, no 4s, no 3s, there's a 2. Then we have 9 0 0 2 0 and pass 4. There is a 8 in that column. So go 5 8 7 1 2. No 7s, no 6s, there's a 5. And then the rest of them in that column are zeros. So maintaining the sequence that they were there, we just copy those down. And on pass 5, sorting, well, let's sort that column. On pass 4. On pass 5, we're going to be sorting the 5th column. We have a 9 there. Starting based on that column. No 8s, no 7s, no 6s, there's a 5. No 4s, no 3s. There's a 2. And there are 2 1s. Copying them down in the order that I encountered them. And after the final pass, then we will have our data in sorted order. Now, to get the time complexity of this sort, each pass is a theta in operation. And you have up to k passes. Where k is known. K is the number of digits, and you would agree before you start using a radix sort that you're only going to include a certain number of digits. You're only going to be sorting on a key that goes up to a certain digits that you agree on. So you have up to k passes, then T of n, or T, you can call it radix sort, of n is equal to theta of kn, which is theta n. So you actually get a theta n sort, but bear in mind that's somewhat cheating if you put it on the same playing field as the comparison-based sorts. The comparison-based sorts can sort anything. That needs its data prepared and formatted before you use the radix sort. Okay, I printed a tutorial 8, but it's not the tutorial 8 that's online right now. The tutorial 8 that's online right now has a lot more diagrams. But since I know that you've been through those diagrams, oh, you have it, great.
If he doesn't have it,
Well,
you have it.
I don't have the full thing, I have a prelim version.
Thank you.
So it doesn't have some of the diagrams with adjacent lists and matrices.
Okay.
It just has the questions, which are what we're doing.
Oh.
So
That's okay.
if I make the assumption that you've been through the other tutorial 8, it's going to be easy. Can I proceed with that assumption?
We've discussed it.
Okay, we've actually discussed all the other tutorials. We have not. You guys didn't turn up to the meeting.
So I had connection problems last night.
Alright, now we've been looking at data structures that include lists and trees, but that doesn't even begin to describe the whole set of data structures that we can use for applications. We can also represent different items with nodes, and the relationship between the different nodes could be considered edges. So if we think of a situation, or if we think of an object like a map, where we may have different places on the map, we can say, okay, each place might have a name, an address, a purpose, and we represent that in a data structure. Now, the distance between one place and another place could be represented on that in a data structure also. So we could actually end up with a whole new set of data structures. To do something like this. Set A, B, C, D, E. For argument's sake. Now, the formal name for those structures are graphs. Now, when you take the whole thing into context, you realize that a lot of the other data structures that we've been looking at are actually subsets, they're actually graphs. Because a tree is actually a graphs, there are nodes and there are edges.